Today, I would like to talk about statistical equilibrium ensembles. I will start with the introduction to the statistical equilibrium ensembles. Then I would like to discuss microcanonical, canonical, and grand canonical ensembles. And at last, I will show the relation of partition function and thermodynamics. It is clearly important to know what the probability density is for a system in equilibrium. This will be a function of the microstate that is a phase space variables. Given such a density, we can then calculate the system entropy using the Gibbs or Shannon entropy functional on such densities, and from this determine most thermodynamic variables of interest in the manner described in the last lectures. This is the basic approach of equilibrium statistical mechanics, which derives a system thermodynamics from the properties of the constituent fine-grained elements. For materials, this means molecules, but can sometimes be extended to more general situations, such as fluids. The particular form of this target probability density will depend on the energetics of the molecules, that is, the precise form of energy. It will also depend on the way in which equilibrium is set up for the large-scale system. Historically, three different configurations have been considered. First, completely closed to the environment. Here, conserved quantities for the dynamical system will be constant in time. Such a configuration is termed microcanonical. Second, open to exchanges of energy only with the environment. If in this system, if the system reaches equilibrium, then the total energy will show very small fluctuations from a mean value. This is due to the energy interchange with the environment. Such a configuration is termed canonical. Third, open to exchange of energy and molecules with the environment. This is an extension of the previous case. Here, both the total energy and the number of particles will be subject to small fluctuation about means of both quantities. This configuration is termed grand canonical. So we have microcanonical for the system close to the environment, canonical for the system open to the exchange energy only with the environment, and grand canonical for the system open to exchange energy and molecules with the environment. Now, as time proceeds in these three equilibrium configurations, the microstates will not be fixed in general, which is the reason for seeking an equilibrium probability density. We hypothesize that this exists and is time invariant. It is sometimes referred to as an invariant measure for the system that is a measure which remains the same under time translations. A large sample of microstates drawn from such a density is commonly called an ensemble and was introduced as an analytical tool originally by Gibbs. Behind it, however, lies the central concept of an equilibrium density or invariant measure. The densities for the three different configurations differ, and the last two are in practice the easiest to compute. In the limit that the number of molecules becomes infinite, they are supposed to converge to each other, and this is called the thermodynamic limit. The closed property of microcanonical ensemble ensures that the system lies always in a particular submanifold of phase space. This is specified by the values of invariance for the system with energy being the most commonly considered. We have energy E of PQ equals E0. This defines a generally closed and compact submanifold C of phase space of dimension 2n-1, where n is the number of particles. Since the system is so constrained, then all probability densities must be defined as non-zero only on this submanifold. The 2n-1 dimensional volume for submanifold C is of central significance to this situation, and we denote it by volume V of C and have integral over submanifold C of 1 is identical to the volume V of C. Now, suppose we have two different densities, P and Q, defined on C, then their relative entropy equals the integral over C of P times logarithm of P over Q, and that is greater than or equal to 0. Now select Q to be uniform on C. This makes sense if C is compact of finite 2n-1 dimensional volume. Now it follows from the relative entropy non-negativity that the integral over C of P times logarithm of P is greater than or equal to logarithm of Q. Then we have that the Shannon entropy S of P is less than or equal to logarithm of 1 over Q, that is equal to the Shannon entropy S of Q. This implies that Q is the density of maximum entropy for the system, and therefore the equilibrium density for the microcanonical ensemble. Next, we have that the equilibrium density for the microcanonical ensemble Q equals 1 over volume V of C, and the entropy S of Q equals logarithm of volume V of C. This formulation of entropy was first proposed by Boltzmann in a slightly different form to take into account the units of phase space volume and to set the temperature unit to degrees rather than joules. Boltzmann hypothesized that the maximum entropy density uniform on C was actually achieved in equilibrium. It turns out that the situation is more complicated than this. Indeed, there can exist members of the microcanonical ensemble that are never visited in any equilibrium configuration. These have, however, Lebesgue measure 0. The hypothesis that all microcanonical ensemble members are equally likely was first stated by Boltzmann and was called the ergodic hypothesis. It was shown to be strictly untrue around 1930, but was replaced by the quasi-ergodic hypothesis, which very roughly means any coarse graining of the submanifold C with equal Lebesgue measure will have equal probability measure. This was proven by Birkhoff and von Neumann in the 1930s. The calculation of the entropy in the case of the microcanonical ensemble can be difficult since it involves the volume of a constrained submanifold. A somewhat easier approach mathematically comes with the more practically realistic case of the canonical ensemble where energy exchange is permitted with the environment. As a consequence, when equilibrium is achieved, total energy fluctuates slightly since molecules inside and outside the system of interest are always exchanging energy. Some reflection indicates, however, that as the number of molecules gets larger, such fluctuations become smaller. In the thermodynamic limit, as the number of molecules becomes infinite, these fluctuations approach 0, and the canonical and microcanonical ensembles converge. We make the assumption that the equilibrium density is invariant under time translations, which seems reasonable for a statistical equilibrium. It follows now that the expectation value of total energy with respect to the equilibrium density is also invariant. From this, we can derive the form of the equilibrium density using the maximum entropy principle, as we did for the microcanonical case. We do this using Lagrange multipliers. Suppose the required probability density is rho of PQ, and assume that the following relations hold. The integral of rho of PQ times energy E of PQ equals mean energy of the ensemble, E0, where the integral is over all phase space. The problem then becomes to find probability density subject to the requirement that the associated differential entropy S is maximized, and given equation is met as well as the normalization condition, the integral of the probability density rho of PQ equals 1. Let the Lagrange multiplier for the energy constraint be lambda 1 and that for the normalization condition be lambda 0, and maximize the augmented functional with respect to rho. We have J is identical to the minus integral of probability density rho times logarithm of rho plus Lagrange multiplier for the energy constraint lambda 1 times integral of rho times energy E minus mean energy of the ensemble E0 plus Lagrange multiplier for the normalization condition lambda 0 times the integral of rho minus 1. Taking the functional derivative with respect to rho and setting to 0, we get minus logarithm of probability density rho minus 1 plus lambda 1 times energy E plus lambda 0 equals 0. This implies that the maximum entropy distribution must have the form the inverse partition function z of lambda 1 times exponential of lambda 1 times E of PQ. Partition function here is need to ensure that rho is normalized as a density and have a form the integral of exponential of lambda 1 times E of PQ dq dp, and that equals exponential of 1 minus lambda 0. The maximum entropy density has precisely the form deduced a few weeks ago using the steady Liouville equation and the additivity of system invariants across subsystems. The density in these equations is of central importance to equilibrium statistical mechanics and is called the Gibbs density. Empirically, it can be shown to apply in many different systems of practical interest. It is particularly convenient since it requires only knowledge of the system's total energy as a function of phase space coordinates. Notice that there is a different Gibbs density for each choice of lambda 1. We can interpret this parameter by holding it fixed and calculating the entropy. S minus S ref equals minus integral of probability density rho times logarithm of rho equals logarithm of partition function z minus Lagrange multiplier for the energy constraint lambda 1 times mean energy of the ensemble E0. Now, the E0 is the thermodynamic energy, so for the equilibrium system under consideration, the ds over dE0 equals 1 over t, and that equals minus lambda 1. Thus, the Lagrange multiplier is simply minus the reciprocal of the system temperature. Note also that the partition function z is an important part of the entropy and is a non-obvious function of the inverse temperature via the given equation and the total energy function of the phase space coordinates. Grand canonical ensemble is the most realistic situation in which the open system exchanges both energy and molecules with the environment, but has a steady equilibrium density. The mathematical formulation is a little more technically complicated since the phase spaces of systems with different numbers of molecules have differing dimensions, but this is not important to the final result obtained. Defined an outcome space X equals tensor product of natural set and 3 coordinate space to the infinite, and the probability density P, which satisfies the restriction that probability density P of nx equals 0 when x is not an element of R to the 2n, which is a subset of R to the infinity. N here is the number of molecules, and R to the 2n consists of real sequences with zeros beyond the 2n position. A further complication concerns the phase space of identical particles. If one permutes identical particles, then the microstate obtained remains the same. To avoid multiple counting of the same microstate, one divides phase space volumes by the number of possible permutations, the factorial of n. The concept of indistinguishability of particles is fundamentally a quantum one, since in classical mechanics, one could in principle label each molecule and keep track of them. This is not possible in quantum mechanics. We therefore weight volume elements in phase space as follows. dV equals d to the np times d to the nq divided by the Planck's constant to the 3n times the factorial of n. Planck's constant has also appeared for dimensional consistency. Now the mean of molecules n is equal to the sum from n equals 0 to infinity of the integral over r to the 2n of number of molecules n times the probability density p of nx dV. The expected energy E equals the sum from n equals 0 to infinity of the integral over r to the 2n of energy E of nx times the probability density p of nx dV. The normalization condition for the density p is 1 equals the sum from n equals 0 to the infinity of the integral over r to the 2n of the probability density p of nx dV. For a time invariant p, these expectations must always be fixed, and some macrostates are specified using both the mean number of molecules and the mean energy. We can now solve the maximum entropy constraint optimization problem with 3 constraints rather than 2, and obtain in a similar way to the canonical ensemble. Minus logarithm of the probability density p minus 1 plus lambda 1 times energy E of nx plus lambda 2 times n plus lambda 0 equals 0. Thus, we obtain that the probability density p of nx equals the inverse partial function zg times exponential of lambda 1 times energy of nx plus lambda 2 times the number of molecules n. In this case, the inverse partial function, the partial function zg of lambda 1 and lambda 2 is identical to the sum from n equals 0 to infinity of the integral over r to the 2n of exponential of lambda 1 times energy E of nx plus lambda 2 times the number of molecules n dV. In a similar fashion to the canonical ensemble, probability density p may be shown to achieve the maximum entropy. Also, in a manner similar to the canonical ensemble, we can calculate the entropy and after differentiation by the mean number of molecules, obtain that lambda 2 equals me over t. Hence, this second multiplier is related to the chemical potential of the system. As we have seen for the canonical ensemble, the partition function of lambda 1 is an important component of the Gibbs density. It can be related in an interesting way to a thermodynamic potential. Combining these equations, we get up to a constant reference entropy that logarithm of the partition function z equals temperature T times entropy S minus mean energy E0 over temperature T, and that is equal to minus Helmholtz free energy F over temperature T. Now, in general, the partition function Z will depend on both temperature T, since this is minus the inverse Lagrange multiplier, as well as the volume V of the system, since the integral used to obtain the partition function Z depends on integrals over the locations of molecules. Thus, if we are able to calculate the partition function for a particular system, then we also have the free energy F as a function of temperature and volume. We are then able to compute pressure and entropy by simple partial differentiation, and we have the full set of thermodynamic variables for the system. A similar procedure extends this to the grand canonical ensemble, where the chemical potential makes an appearance as a further thermodynamic variable. For the canonical ensemble, the calculation of the partition function depends crucially on the form of the total energy, which for many systems can be decomposed into 2 pieces, kinetic and potential energy. The kinetic energy is a simple quadratic form for the momenta, and so the integral over this part of phase space is the integral of a Gaussian function. Most of the work usually occurs in integrating the potential energy over the molecular position variables. For an ideal gas, this potential term vanishes. We will consider this case in the next lecture. And on this, I would like to end today's talk. Thank you.